So this chapter is over the kinetic theory of matter. The kinetic theory of matter is really about the idea that matter is composed of tiny particles of finite size. In other words, atoms and molecules. This theory came about in a variety of ways and slowly over time. But the idea that we experience pressure and temperature, these are actually the effects of small particles bouncing off each other and or exchanging kinetic energy and so forth. And so the kinetic theory of matter is really about how the motion of tiny particles gives us things like pressure and temperature. Early in the science days, this is Robert Boyle, and this is called Boyle's Law. Boyle recognized Robert Boyle. He lived from about I have it written down 1627 to maybe 1691, I think, maybe something like that. And he contributed a bunch of things to physics and chemistry. But what he noticed was that if you kept the number of molecules, in other words, if you had a sealed container and you kept the temperature constant, then pressure was inversely proportional to volume. In other words, if you increased the pressure, the volume got smaller. If you decreased the pressure, the volume got larger, if these two things were constant. Charles, who lived from, I think, 1746, I have it here, to 1823. His name was Jacques Charles. Boyle was English, Charles was French. He noticed that volume was proportional to temperature if you kept the number of molecules constant and you kept the pressure constant. And then finally, Amundsen or Gay-Lussac, I don't know too much about these guys, pressure is proportional to temperature for constant volume and constant number of molecules. In other words, if you have a container and you increase the temperature, in other words, you heat it, the pressure will increase proportionally, and so forth. And so these were the three laws that existed. I don't know when these guys lived, but say by the early 1800s, this was sort of known. And this led to the ideal gas law, which you've probably seen. This is PV equals NKT. And you probably remember that, if you want to change proportionality to an equal sign, you just have to put a constant. Something if V is proportional to T, then V is equal to some constant times time. And so that's what this satisfies all those equations. For example, if number of molecules and temperature is constant, in other words, if all this is constant, then P is inversely proportional to V. In order for these two to be equal to a constant, if P gets big, V has to get proportionally smaller. Each one of these is true. If the pressure is constant and the number of molecules is constant, then V is proportional to T, and so on. So let me identify these. We said P equals pressure. We've already talked about pressure. V equals volume. T equals temperature. It has to be an absolute temperature. So for SI, that's going to be Kelvin. But there are English versions of the absolute temperature, like Rankine for Fahrenheit. N equals number of molecules. And so that's how many molecules there are in there. And finally, K, sometimes it's written as KB. And this is 1.38 times 10 to the minus 23 joules per Kelvin. And that's called the Boltzmann constant. So this takes into account all of these. Okay. So let's do an example. So a bicycle tire has 7 times 10 to the 5th pascals. Remember, 10 to the 5th pascals is about 1 atmosphere, and so it's about 7 atmospheres of pressure. Again, these have to be absolute numbers in the ideal gas law. So if this is a gauge pressure, then you'd have to add an atmosphere to it to get the absolute pressure, assuming it was, sitting on the surface of the Earth. Right, and so we're going to say at T equals, not little t, temperature, T equals 18 degrees Celsius. And then we could say tire pressure is 7 times 10 to the 5th pascals at 18 degrees Celsius, assuming the volume is constant. In other words, the tire heats up a little bit. It's going to expand a tiny bit, but we're going to say it's negligibly small. We're going to say, what is the pressure when the temperature equals 35 degrees Celsius? So we've kind of got a before and an afterwards thing. And so we're going to call this T1 and T2 and P1 and P2. So we want and so we have the ideal gas law. We have PV equals NKT, right? And so we could rewrite this way. We could say, look, P over T equals NK over V. And in both cases, in the first case and in the second case, the number of molecules and the volume are not changing, right? If I've got a tire that's sealed up, no more air molecules are getting in or out, and it's already said, even though the pressure changes slightly, we're saying that the volume change is negligible. And so look, I can say P1 over T1 is equal to NK over V. But I also have P2 over T2 is equal to N times K over V. The number of molecules doesn't change when the temperature goes up. Boltzmann's constant doesn't change. V doesn't change. And so that means P1 over T1 equals P2 over T2. Right. We're looking for P2, so I can say P2 is equal to T2 over T1 times P1, right? And now I have to be careful to use absolute temperature, not Celsius. And so I would say that's equal to, so T2 is 35, so in Kelvin that's 308, right? Because you add 273 to that, Kelvin, over 18, 8191, 291 Kelvin, times 7 times 10 to the 5th pascals. And so P2 7 times 10 to the 5th pascals. 7.4 times 10 to the 5th. So in this question, we're going to ask how many molecules are in a cubic centimeter of air at 273 Kelvin and 1 atmosphere, right? So 1.01 times 10 to the 5th pascals. In other words, how many molecules are approximately in a cubic centimeter of air, right? And so we have the ideal gas law, and that means that N is equal to PV over KT. Right, and that's 1.01 times 10 to the 5th pascals. Now I have to get a centimeter cubed, I want to convert that into meters cubed, and so I'm going to say 1 centimeter cubed times 1 meter over 100 centimeters all cubed. Right? And so that's PV. And then it's 1.38 times 10 to the minus 23 joules per Kelvin times 273 Kelvin. I get about 1.34 times 10 to the 16th molecules. And so, a billion is 10 to the 9th, a trillion is 10 to the 12th, a quadrillion is, let's see, a billion is 10 to the 9th, a trillion is 10 to the 12th, a quadrillion is 10 to the 15th. So 13.4 quadrillion molecules in 1 cubic centimeter. Gives you a sense of how small a molecule is. So let's talk about Avogadro's number for a minute. Avogadro's number is a mole, which is the number of molecules in 12 grams of carbon-12. Right? It's also the number in 14 grams of carbon-14, or 16 grams of oxygen-16, or 44 grams of CO2 with the corresponding isotopes, and so on. If you have the number of grams that's equal to, in number to the number of atomic weight, in atomic weight units, you'll have a mole of them. And so Avogadro's number is often written this way: Na is equal to 6.02 times 10 to the 23rd per mole. Right? That's the number of molecules in a mole, right? Or the number of anythings in a mole. Amadeo Avogadro lived from 1776 to 1856. So a useful thing to do with this is to employ Avogadro's number when talking about gases, so that we're not working with enormous numbers of molecules, but a little more reasonable number. And so we can take the gas law as we have it so far, and we can divide and multiply by Avogadro's number. So that I haven't changed the value of this because I've divided and multiplied by Avogadro's number. This is just the number of moles. Right? If this is half as big as that, then I get 0.5. If this is twice that, I get 2, and so on. We usually use a lowercase n for that. This quantity here is the universal gas constant. It's often called R, right? R is equal to Na times Kb, which is 6.02 times 10 to the 23rd times 1.38 times 10 to the minus 23rd joules per Kelvin, which is about 8.314 or something like that joules per mole Kelvin. And that's the ideal gas constant. And so then the ideal gas law equation becomes PV equals nRT, where n is the number of moles, a more manageable number, right? And this is the universal gas constant. So in this problem, we want to determine the density of air at standard temperature and pressure, and that means the temperature is 273 Kelvin, and the pressure is 1.01 times 10 to the 5th pascals. And so if you remember, the density is the mass divided by the volume. And so we're going to try to we're just going to set V equals, V could be anything since we just want the density, and so we're going to start with just a cubic meter, right? And so we'll pick our volume, and so we're going to figure out the mass of air that's in a cubic meter at standard temperature and pressure. And the way we're going to do that is first we're going to figure out how many moles of air is in a cubic meter. And so we can start with the ideal gas law, PV equals nRT. And then we can say, look, N is equal to, I have to do my math here, PV over RT, right? And that's 1.01 times 10 to the 5th pascals times 1 meter cubed divided by 8.31 joules per mole Kelvin times the temperature, which is 273 Kelvin. And what I get for that is N is equal to 44.5 moles. Sorry, we want to calculate the mass. We want to calculate the mass in 1 cubic meter. And that's equal to the number of moles times the molar mass of air. Right? The number of the molar mass is equal to, the number of kilograms, say, per mole. And so if this was, if air we just said was pure nitrogen, it would be 28 grams per mole, or 0.028 kilograms per mole. Again, we're trying to find this M here. M is, we figured out what the number of moles is, so now we've got to figure out the molar mass of air. It's not the same as nitrogen, because nitrogen's 28, but the air isn't pure nitrogen. And so the molar mass of air is just the weighted average of what's in it. And so it's 0.78 times the molar mass of nitrogen plus 0.21 times the molar mass of oxygen plus 0.01 times the molar mass of argon. And that's because the air is 78% nitrogen, 21% oxygen, 1% argon, and then other stuff. And so this is 0.78 times the molar mass of nitrogen is what we just said a minute ago, 0.028, 8 kilograms per mole, plus 0.21 times the molar mass of oxygen, which is 0.032 kilograms per mole, plus the molar mass of argon, 0.01 times molar mass of argon, which is 0.40 kilograms per mole. If you add all that up, you get 0.029 kilograms per mole. And so that's the average molar mass of air. It's just a weighted average of all the guys that are in it. And so that means the mass is, our M is 44.5 moles times 0.0, let me try that again, 0.029 kilograms per mole, which is 1.29 kilograms. And so that's the mass of 1 cubic meter of air. And so the density is the mass divided by the volume, and so that's 1.29 kilograms over 1 cubic meter, or 1.29 kilograms per cubic meter. That's the density of air. You can sort of look at this and say, if you remember, the density of water is a gram per cubic centimeter, which comes out to be 1,000 kilograms per cubic meter, right? If you do that math. And so the density of air is about 1,000 times smaller than the density of water. And what that means is that on average, the molecules are about 10 times farther apart in each dimension. 10 times farther apart this way, 10 times farther apart that way, and 10 times farther apart this way in the vertical direction, sort of towards the camera. And a factor of 10 in each of those directions produces a factor of 1,000 in the density. And so it gives you a rough idea of how much farther apart air molecules are than say, molecules in a liquid or a solid, where they're kind of right up against each other, so to speak.